NFPA 70, the National Electrical Code, mandates overcurrent protection for all circuits and equipment to prevent electrical fires and equipment damage. Unfused disconnects offer isolation only, and they do not protect against short circuits. Fused disconnects, conversely, provide both isolation and short circuit protection. When evaluating the need for fused disconnects, there are practicality considerations. Fused disconnects are generally more expensive than unfused disconnects. Also, fused disconnects often require more space and enclosures compared to unfused disconnects. Internal disconnect switches within equipment offer convenience for isolation, but may not provide the same level of short-circuit protection as separate fused disconnects. For new installations, it's generally best practice to install fused disconnects at 480 volts equipment, even if the equipment already has an internal disconnect switch. This ensures that the circuit is properly protected against short circuits and complies with electrical codes. Always consider the amp interrupting capacity, or AIC rating, of the equipment when selecting the fused disconnect. For existing installations, if the equipment has an internal disconnect switch but no external fused disconnect, it is crucial to evaluate the risks and potential consequences of not having short-circuit protection. If the risk is deemed significant, consider installing an external fused disconnect. However, if the internal disconnect switch is adequately rated for the available short-circuit current, it might be acceptable to forego an external fused disconnect. Always verify this with the equipment manufacturer and local authorities to ensure compliance and safety. There are exceptions to the general rule of using fused disconnect. Firstly, in ultra-high impedance or high-Z systems, fused disconnects may not be necessary. This is because the short-circuit current is inherently limited by the design of the system. Secondly, for equipment with a limited short-circuit capacity, if the equipment has a limited short-circuit capacity that falls below the AIC rating of the internal disconnect switch, external fused disconnects may not be required. It is very important to foster communication and collaboration throughout the decision-making process regarding the installation or non-installation of fused disconnects. This includes involving all relevant stakeholders such as equipment manufacturers, installers, inspectors, and facility managers. The goal is to ensure everyone understands the reasoning behind the choices made and the implications for safety and compliance. The amp interrupting capacity, or AIC rating, is a critical parameter when selecting overcurrent protection devices, like fuses and circuit breakers. It signifies the maximum short-circuit current that a device can safely interrupt without failing or causing an arc flash. Understanding and properly applying AIC ratings is crucial for ensuring electrical safety and preventing equipment damage. When evaluating the available fault current at a specific point in an electrical system, engineers use various methods including calculations, software simulations, and on-site measurements. These assessments take into account factors such as the utility source impedance, transformer characteristics, conductor sizes and lengths, and the presence of any current limiting devices. The calculated fault current must be less than or equal to the AIC rating of the protective devices installed at that location. If the available fault current exceeds the AIC rating of a fuse or circuit breaker, the device may not be able to safely interrupt the fault. This can lead to catastrophic failure, resulting in equipment damage, electrical fires, and potential injury to personnel. In such cases, it is necessary to upgrade the overcurrent protection devices with higher AIC ratings or implement other measures to reduce the available fault current. Several factors influence the available fault current in an electrical system. Firstly, the utility source impedance plays a significant role. A lower source impedance results in a higher available fault current. Secondly, the size and impedance of transformers impact the fault current. Larger transformers with lower impedance contribute to higher fault currents. Thirdly, the length and size of conductors affect the fault current. Longer conductors with smaller cross-sectional areas increase impedance, thereby reducing the available fault current. Fourthly, the presence of current-limiting devices, such as fuses and reactors, can significantly reduce the available fault current. There are several methods to mitigate high fault current levels in electrical systems. Firstly, current limiting fuses can be used. These fuses are designed to rapidly interrupt fault currents, limiting the let-through energy and reducing the stress on downstream equipment. Secondly, current-limiting circuit breakers offer similar protection as current-limiting fuses but can be reset after an interruption. Thirdly, reactors can be installed to increase the impedance of the circuit, thereby reducing the available fault current. Fourthly, transformers with higher impedance can be used to limit the fault current. Fifthly, upgrading conductors to larger sizes can reduce impedance and slightly decrease the fault current. Sixthly, service entrance equipment with higher AIC ratings can be installed to accommodate high fault current levels. The National Electrical Code, NEC, provides specific guidelines for selecting and applying overcurrent protection devices based on their AIC ratings. NEC Section 110.9 addresses the interrupting rating, requiring that the equipment intended to interrupt current at fault levels be rated for the available fault current at its supply terminals. NEC Section 240.86 covers series ratings, allowing the use of overcurrent devices with lower AIC ratings if they are applied in series with an upstream device that has a higher AIC rating and the combination is tested and listed for series operation. NEC Section 240.60 details the requirements for fuse holders, specifying that they must be designed to accommodate the class and voltage rating of the fuses used. The underwriters' laboratories, all provide standards for testing and listing overcurrent protection devices, ensuring that they meet specific performance and safety requirements. EUL Standard 248 covers low-voltage fuses, specifying the test procedures and performance criteria for various fuse classes. UL Standard 489 covers molded case circuit breakers and circuit breaker enclosures, defining the requirements for interrupting capacity, endurance, and other performance characteristics. UL Standard 1558 covers medium voltage metal enclosed switchgear and control gear, including requirements for short circuit testing and AIC ratings. Proper coordination of overcurrent protection devices is essential for ensuring that faults are cleared quickly and selectively, minimizing the impact on the rest of the electrical system. Coordination studies involve analyzing the time current characteristics, or TCC curves, of different protective devices to ensure that the device closest to the fault will operate first, while upstream devices remain unaffected. Time current characteristic curves illustrate the time it takes for an overcurrent device to trip at various current levels. These curves are used to determine the coordination between different devices in a system. Coordination studies typically involve the use of software tools that simulate fault conditions and analyze the performance of overcurrent protection devices. These studies help identify potential coordination problems and ensure that the system is designed to provide optimal protection. Short circuit studies are performed to determine the magnitude of fault currents at various points in an electrical system. These studies are essential for selecting overcurrent protection devices with adequate AIC ratings and for coordinating the protection system. Short circuit studies take into account factors such as the utility source impedance, transformer characteristics, conductor sizes and lengths, and the presence of any current limiting devices. Arc flash studies are conducted to assess the potential hazards associated with arc flash events. These studies calculate incident energy and arc flash boundary at various locations in the electrical system. Arc flash studies are used to determine the appropriate personal protective equipment, or PPE, requirements for workers who may be exposed to arc flash hazards. Risk assessment is a critical component of electrical safety management. It involves identifying potential hazards, evaluating the likelihood and severity of potential incidents, and implementing measures to mitigate the risks. Risk assessment should be conducted regularly to ensure that the electrical system is safe and that workers are protected from hazards. The electrical safety program should include comprehensive training for all personnel who work on or near electrical equipment. Training should cover topics such as electrical hazards, safe work practices, personal protective equipment, and emergency procedures. Regular refresher training should be provided to ensure that workers maintain their knowledge and skills. Lockout-tagout procedures are essential for preventing accidental energization of equipment during maintenance or repair. These procedures involve isolating the equipment from all sources of energy and applying locks and tags to prevent it from being inadvertently turned on. Lockout-tagout procedures should be followed meticulously to ensure the safety of workers. Personal protective equipment, or PPE, is necessary to protect workers from electrical hazards such as arc flash, electric shock, and burns. Common types of PPE include arc-rated clothing, insulated gloves, safety glasses, and hard hats. The appropriate PPE should be selected based on the specific hazards present in a work environment. Electrical safety audits are conducted to assess the effectiveness of the electrical safety program and to identify any areas that need improvement. Audits should be conducted by qualified personnel and should cover all aspects of the electrical system, including equipment, procedures, and training. Regular maintenance and testing of electrical equipment are essential for ensuring its safe and reliable operation. Maintenance activities should include visual inspections, cleaning, lubrication, and testing of components. Testing should be performed in accordance with manufacturers' recommendations and applicable standards. Grounding is a critical safety measure that provides a low impedance path for fault currents to return to the source. Proper grounding helps to prevent electric shock and equipment damage. Grounding systems should be inspected and tested regularly to ensure their effectiveness. Electrical panels should be clearly labeled to identify the circuits and equipment they serve. This helps to prevent accidental energization of the wrong equipment and facilitates troubleshooting. Warning signs should be posted in areas where electrical hazards exist. These signs should clearly communicate the nature of the hazard and the precautions that should be taken. Emergency procedures should be established for responding to electrical incidents such as arc flash, electric shock, and electrical fires. These procedures should be clearly communicated to all personnel and should be practiced regularly. Incident investigation is essential for identifying the root causes of electrical incidents and for implementing corrective actions to prevent recurrence. Incident investigation should be conducted by qualified personnel and should involve a thorough review of the events leading up to the incident. Electrical safety standards are developed by organizations such as the National Fire Protection Association, NFPA, the Institute of Electrical and Electronics Engineers, IEE, and the American National Standards Institute, ANSI. These standards provide guidelines for the safe design, installation, and maintenance of electrical systems. Compliance with electrical safety standards is essential for protecting workers and preventing electrical incidents. The Occupational Safety and Health Administration, OSHA, is responsible for enforcing electrical safety regulations in the workplace. OSHA conducts inspections of workplaces to ensure compliance with its regulations. Failure to comply with OSHA regulations can result in fines and other penalties. It is crucial to stay up to date on the latest electrical safety standards and regulations. This can be achieved by attending training courses, reading industry publications, and participating in professional organizations. Staying informed about electrical safety helps to ensure that the electrical system is safe and compliant. Proper documentation of the electrical system is essential for effective management and maintenance. Documentation should include as-built drawings, equipment specifications, maintenance records, and inspection reports. Accurate and up-to-date documentation facilitates troubleshooting and ensures that the electrical system is operated and maintained safely. A well-designed and maintained electrical system is essential for the safe and reliable operation of any facility. By following best practices for electrical safety, organizations can protect workers, prevent electrical incidents, and ensure the continuity of their operations. Remember that electrical work should only be performed by qualified and trained personnel. Always follow safe work practices and use appropriate personal protective equipment.